Hello and welcome to the discussions that we will have via video on advanced engineering mathematics differential equations. So there will be about 3.5 chapters that we will cover in differential equations. It's certainly not a substitute for a full differential equations class, but we'll try in these lectures to hit the highlights of differential equations and that are important to at least being able to put you in a position where you can do further and additional review. So, with no further ado, the textbook that we're using is Advanced Engineering Mathematics by ZILL, Z-I-L-L, and publisher is Jones and Bartlett Learning, and we're going to start right off with Chapter 1. So an outline for Chapter 1 is shown above. In this lecture, we'll discuss definitions and terminology. So a differential equation is an equation that contains a variable, a dependent variable, and one or more of its derivatives with respect to one or more independent variables. And we can classify them in a number of ways. And so the three different ways that differential equations are classified are type, order, and linearity. So starting out with type, there are two different types of differential equations: ordinary differential equations, or ODEs, and partial differential equations, or PDEs. So if you look at the equation here under ordinary differential equations, you can see first of all what shows up is this x, and x, notice, has a derivative with respect to t that shows up in this equation, as does y. So first of all, it's completely possible to have more than one independent or dependent variable, x and y, but in an ordinary differential equation, you only have one independent variable. So notice everything is differentiated with respect to time. You could also have second or third derivatives showing up in this equation as well, as long as they're with respect to time. So the solution to this is going to look like x is equal to some function of time and y is equal to some function of time. Now, a partial differential equation, basically you have derivatives that are with respect to two or more independent variables. And I want to point out, first of all, in the textbook materials, there is an error in the notation here. You notice in all of these derivatives, we have this script d. Notice in this derivative, we have a printed d. So that's just an error. That should also be a script, because that script, that notation, is what basically indicates to us that we have a partial derivative. The reason it's a partial derivative is that both u and v here could be a function of x and y. And so what we're expressing here is that we're taking the derivative of u with respect to y only. And what we're expressing here is we're taking the derivative of v with respect to x only. Now, if you've never had multivariate calculus where you're taking derivatives with respect to different variables and you have more than one independent variable in your equation, what you do when you take the partial of a function with respect to y is everything else, including all the other independent variables in the taking of this derivative, are treated as constants. All right, so the notation, there are a number of different types of notation. The ones that you will see the most often are the Leibniz notation, which shows the differential operator d. The prime notation is also not uncommon. We don't see Newton's dot notation very often. Sometimes you do in textbooks, particularly mathematics textbooks, sometimes in physics textbooks, you'll see this. But not as often as the first two types of notation. And the subscript notation for partial derivatives is very unusual once you get outside of a math class, but did want to show you this just in case, because there are some people in engineering and some subfields within engineering where this notation does show up as well. All right, we can also classify differential equations by order. So the order is a definition that applies across both ordinary and partial differential equations, and basically the order will be the highest order of derivative. So if we look at this equation on the left, you'll notice that this first term is a second derivative with respect to y. The second term is a first derivative with respect to y, and then whatever that result is is cubed. It is not a third derivative. So the order of this equation on the left, it is a second order differential equation, and it's ordinary because of the notation. Over here on the right, we have u, which is our dependent variable. It's a function clearly of both x and t. So this is a partial derivative equation, or partial differential equation. Notice we have partial derivative, the fourth partial of u with respect to x. So it doesn't matter that there's a change of variables here. It's defined by its highest order, which in this case is 4. So the one on the left is a second order differential equation. The one on the right is a fourth order differential equation. Classification by linearity. So we classify differential equations as to whether they are linear or nonlinear. In a linear differential equation, you'll have a function of the independent variable and then the dependent variable and all of its derivatives. You're able to set that equal to 0. We call that linear as long as whatever that function is a linear function. So sometimes it's easier to specify what is linear and what is by talking about what is nonlinear. So it's nonlinear if the coefficients or multipliers of y and its derivatives contain y and its derivatives, or if y and its derivatives are raised to a power, or if they're a part of a nonlinear function like the sine of y or e to the y prime, and that appears in the equation. So these are all things that would make this nonlinear. If we go back to that previous example where we had the partial of y with respect to x, so this is a first derivative, but then it's cubed, that automatically makes this a nonlinear differential equation. Notice that the independent variable, e to the x, that's okay. That does not make it a nonlinear differential equation. The other thing to mention that's not really mentioned in this book is the difference between homogeneous and inhomogeneous. So let me go back to an earlier example. Here, and this is not a great example, but let me just use this as an example. In this case, we have x and its derivatives, we have y and its derivatives, but we don't have anything else. So we could put all of the x's and y's on one side of the equation, and we would only have dependent variables and their derivatives, and that would equal 0. That's referred to as a homogeneous equation. Let's suppose that we had this and we had a term in here, maybe a constant, maybe we say plus 10, maybe plus the sine of t, the independent variable. That would make this then an inhomogeneous differential equation. And we'll talk a lot more about that later. But in many traditional textbooks, they talk not so much about ordinary and partial as being a classifier, but order, linearity, and homogeneous. So you will hear people say things like, this is a second order linear homogeneous differential equation. All right, so back to where we were. The solution of an ordinary differential equation. So there's some math terminology here. Most differential equations have what we refer to as a trivial solution. So most differential equations, 0 is a solution somewhere on some interval. So the trivial solution we generally ignore. We also tend to talk about functions being defined on some interval, and that the derivatives on that interval are continuous. And so basically, if we take this function phi, which is continuous on some interval, and its derivatives are also continuous, and we substitute it into an nth order differential equation, basically the statement of the differential equation becomes true. In other words, the solution works. So it's kind of a practical definition. We're just saying a solution is any function that if you substitute it into the differential equation, it works to create 10 equals 10 or 1 equals 1 or x equals x or some identity function. The interval can be an open interval, meaning it includes it has endpoints. It can be a closed interval. It can be an infinite interval. This is not, one of the things that's super important most of the time until you get to very specific definitions, but wanted you to just understand what that actually means. So the solution is a solution curve because basically because we have derivatives. Remember, if you have a function and it contains a constant and you take its derivative, the constant goes to 0. So when we solve a differential equation, we're going the other direction. We're actually, in some ways, integrating. So in a first order differential equation, we'd be integrating, but unless it is somehow specified with the boundary condition, we don't really know what that constant was that got differentiated out. So because of that, we sometimes get what we refer to as a family of curves. An explicit solution is one in which the dependent variable is expressed solely in terms of the independent variable and its constants. An implicit solution is if you just have a function phi that satisfies the relationship, the relation g of x and y, and the ordinary differential equation on some interval I. So we just talked about families of solutions that basically we will have a function that satisfies the differential equation. We could add any constant to that function and it will still satisfy the differential equation because as soon as the function was differentiated, the constant went out. So a solution with a constant c basically represents a family of curves, and we refer to c as a parameter. If we have an nth order differential equation, we will get an n parameter family of solutions because each time the function is differentiated, it is possible that an additional constant becomes differentiated away. So each time we integrate, so if we have a third order differential equation, basically we would have to integrate that 3 times to get that differential to go away. And in the process of doing that, we would generate up to 3 constants of integration. So that's known as a parameter. Usually in the real world, in engineering, we have certain boundary conditions, and that enables us to be able to solve for and find the parameter. Systems of differential equations. When you have 2 or more equations that involve the derivatives of 2 or more unknown functions of a single variable. So here's an example of a system of equations. So we have the derivative of x with respect to t, and that's some function of x, y, and t. We have the derivative of y with respect to t, and that's some function of t, x, and y. So a solution of the system is a set of functions that satisfies each equation in the system of equations. And then finally, let's talk about initial value problems, but I want to address this in the second lecture because I don't want these videos to get too long. So that is where we will begin with the next set of lectures.